In the next set of videos, we'll look at the mathematics behind real AI products like Netflix, Google, and all of that. So here we're starting out with how Netflix predicts what you will watch. How Netflix predicts what you will watch. So here we'll be talking a lot about recommendation systems and matrix factorization. So first of all, imagine that Netflix has 10 million users and 20,000 movies and shows with billions of interactions. And Netflix wants to answer questions such as what movie should this user watch next? The fundamental problem is you have to match a user with a movie to have a predicted preference. So a recommendation system then learns patterns from previous interactions and uses them to make predictions about unseen items. So, in fact, the same can be said of YouTube, right? If you go to YouTube for the first time on your browser, say, and so when you get to the YouTube page, you see that it is blank. But by the time you watch one, two, three, four, five videos, going forward, you'll be recommended what to watch based on the things you had watched. So a recommendation system learns patterns from previous interactions and uses them to make predictions about unseen items. One of the most important mathematical tools for this problem is what is called matrix factorization. Matrix factorization allows us to discover hidden characteristics of users and movies from a large collection of ratings or interactions. So let's go on this journey to do this. Now, the recommendation problem is what we are dealing with here. That's the recommend when we talk about recommendation systems. So the recommendation problem, suppose we have five users and six movies. Each user has watched or rated some of the movies. For example, Alice has watched Matrix and rated it 5. Alice has watched Titanic and rated it 4. Alice watched Toy Story and rated it 5. Bob watched Matrix, rated it 4. Bob watched Titanic, rated it 2. Bob watched Toy Story and rated it 1. Then Bob watched Matrix and rated, Carol rather, watched Matrix and rated it 1, watched Titanic, rated it 5, and watched Toy Story, rating it 2. So the goal is to predict ratings that we have not observed. For instance, how will Alice rate Interstellar? That's the question. So if the model predicts that uh, uh, Alice will rate Interstellar 4.7, then Interstellar becomes a strong recommendation for Alice. So based on Alice's behavior on previous movies, then we now talk about the user item matrix. We can represent the data using a matrix. Row represents users, while columns represent movies. So the entries represent ratings. So for example, you have this user item matrix now. So this row one represents a particular user. Row two is another user. Row three is another user. Row four is another user. While this column one is a movie. So this is movie one, movie two, movie three, movie four, movie five. So the rating of user one for movie one is 5. User one for movie two is 4. User one for movie three is 5. Then we now are thinking, how will user one rate movie four and 5? Then we have for this second user now, he has rated movies 1 to 4, but we want to see how he or she will rate movie 5, and so on and so forth. So the question marks represent unknown preferences now. So like that. So these are movies the users have not watched and they've not rated. The question marks represent unknown preferences. This is called a user item interaction matrix. So the matrix can be extremely large, for as a matter of fact, because I mean, for instance, YouTube or Netflix has tons of movies and shorts and things like that. So for example, you can have a 10 million by 20,000 dimensional matrix, and most entries are actually unknown because I mean, maybe out of the 10 million, there are 20,000 users and there are 10 million things to view. Maybe every an average user probably has seen just about 10,000 of those things. So most of the entries will be unknown if you draw a user item matrix in that case. So most entries are unknown, and this creates the central problem. How can we predict the missing entries? All these missing question marks now. How do we actually get to predict them? Now, the matrix is mostly empty, like we said. So suppose there are 10 million users and 20,000 movies. Okay, okay, yeah, 10 million users and 20,000 movies. The total number of possible user movie combinations will be 10 million by 20,000, which is 200 billion. I mean, that is 200 billion possible interactions. But a particular user has watched only a small fraction of all available titles. Therefore, the matrix is called a sparse matrix. So a recommender system must learn. So a sparse matrix, of course, contains so many zeros. Or so many unknowns at least. So a recommender system must learn from the relatively small number of observed interactions and predict the enormous number of missing ones. So we are getting into the brain of how Netflix uh, chooses for you what's most likely going to watch next. Now, the simplest possible recommendation system can be done here. Of course, whatever we are doing here is just a sneak peek at the reality for sure, because the reality is so enormous, to even put down on paper. Before using sophisticated mathematics, consider a simple strategy. Suppose we calculate the average rating of every movie. Say movie A is rated 4.8, movie B is rated 4.5, movie B is rated 4.1, averagely by all the users, all the people that have watched. So we could recommend the highest rated movies easily. So we can easily recommend movie A for whoever, right? But there's a problem. Different users have different tastes, actually. So one user may love science fiction, action, or fantasy, while another may prefer romance, drama, and documentaries. Therefore, popularity alone is not personalization in that case. So we need to learn something about the user's hidden preferences. Now, how do we go about that? We then go to collaborative filtering. A powerful idea is people with similar preferences tend to like similar things. So suppose Alice and Bob have watched many of the same movies. If both strongly like The Matrix, Inception, and Interstellar, then if Bob rather loves another science fiction movie that Alice has not seen, the movie may be recommended, maybe a good recommendation for Alice. This is called collaborative filtering, and that is why you see on YouTube that people with similar interests also watch, or even on Wikipedia, right? You've checked out someone, and down there they'll say people with similar interest in this person also are interested in this following people. As that's kind of collaborative filtering. So the system does not necessarily need to understand the movie itself. Instead, it learns patterns from user behavior. The basic idea is so it matches users to items and items to users and learns relationships between them. Now, the question, what does a user actually like? Suppose Alice rates action movie 5, science fiction 5, romantic comedy 2, and documentary 1. What is Alice's underlying preference? So we could imagine that Alice has hidden characteristics such as action preference, sci-fi preference, romance preference, comedy preference, and drama preference, for instance. So these characteristics may not be explicitly recorded, and they are called latent factors. And the central idea of matrix factorization is this that the central idea of metric factorization is represent every user and every movie using a small number of hidden factors. And that the whole idea of latency comes in here, just like we've seen under image generation. And then we go on to talk about matrix factorization now, which drives home the point about recommendation systems. Suppose our original rating matrix is R, which is which is an element of an R by M of R M by N, where M is the number of users, N is the number of movies. So instead of directly modeling R, we approximate it using R approximately UV transpose, where U is a subset of R M, M by K, and V is an element of R N by K. So the number K is much this number K here is much smaller than both M and N for sure. So for example, we have R being an element of R 1 million by 10,000 might be approximated using U, which is an element of R 1 million by 50. So talking about 50 movies now. Yeah, talking about so you have 1 million people that have watched 50 movies, compared to 1 million by 10,000. And V now is a subset of R 10,000 by 50. So the enormous problem has been compressed into a much smaller latent representation in that case. So we have an idea about 1 million movies watched by 50 people and 10,000 movies watched by 50 people. So the enormous I think I'm switching it. Yeah, 50 movies watched by 1 million people and 50 movies watched by 10,000 people. The enormous problem here has been compressed into a much smaller latent representation. So, and then we can easily do R is approximately UV transpose like that, which then becomes a 1 million by 10,000 thing because this now is transposed. So we have 10 million by 50 multiplied by 50 by 10,000. So that will end up being 1 million by 10,000 that we started out with. Now, how does matrix factorization predict a rating? Now, let U sub I represent user I and let V sub j represent movie j. So the predicted rating R cap sub ij is equal to ui transpose v sub j. In expanded form now, we have this now that r cap sub ij equals u sub i1 v sub j1 plus u sub i2 v sub j2 plus all of that all the way down to plus u sub ik v sub jk. This is simply a dot product. Therefore, recommendation system will be equal to similarity over alignment in latent space like that. So let's do some two latent factors, for instance. Suppose we use only two hidden factors, which is a far cry from reality for sure, but it will help us understand the math at least. For example, you have an action and sci-fi preference, and then you have a romance and drama preference, for instance. So here it talks about similarity slash alignment in latent space. That's what recommendation is about. So imagine action, sci-fi preference, romance, and drama preference. Suppose Alice has the latent factor. You, Alice, is 0.9 for action, 0.2 for romance. It's not a probability distribution, by the way. And then we have movie X. Suppose movie X has VX, that's 0.8 and 0.3. So the predicted rating for Alice would just simply be 0.9 by 0.8 plus 0.2 by 0.3 multiplied by 0.3. Therefore, the ratings Alice might likely give will be R Alice, that's 0.72 plus 0.06. So R Alice for movie X, which she hadn't seen before, will be 0.78. So now what we are saying is Alice has this latent factor. So 0.9 for action, 0.2 for romance. And then we have a new movie, which is 0.8 sci-fi, 0.3 romance. And then we put the whole rating together and we get 0.78. So the absolute value is not yet a 1 to 5 rating because this simple example has not included scaling or biases. So the important idea is simply the dot product in this situation. Like that. Now, let's talk about adding user and movie biases now. Users have different rating habits. Some users give almost everything a high rating. Exactly. Others are extremely strict. So I mean, it's reality, right? Some people are very stingy with ratings, while some are very generous. So others are extremely strict. Movies also have different baseline popularity. Therefore, we introduce mu, which is global average rating, and B sub I, which is user bias. B sub J is movie bias. So the prediction becomes R cap sub ij, that is mu, the global average rating plus the user bias plus the movie bias B sub j, and uh, user bias is B sub I, right? Plus the actual rating we did previously, that is UI transpose V sub j, UI U sub I transpose multiplied by V sub j. So this is a fundamental recommender system equation. Interpretation here, so for to get a prediction, you look at add the global average to the user tendency, to the movie tendency, to the user movie interaction like that, and then you get a rating. So to have a numerical example, suppose the global average is 3.5. So a movie is rated globally 3.5, and Alice's bias, that's the user tendency, is 0.3. Movie's bias is 0.4. So Alice's latent vector will be is now like 0.8, 0.6 for the for a type of movie, and then the movie's latent factor is 0.7, 0.5. So this would give us the interaction between Alice and the movie X. Now we first calculate the dot product, which is 0.8 times 0.7. So you see the idea of the dot product has become very useful here. So that simple trick we learned in vectors has become so useful in this whole thing. So you have 0.8 times 0.7 plus 0.6 times 0.5. So you have 0.56 plus 0.30, which ends up being 0.86. But that's just the user movie interaction. So we then add up every other thing. So therefore, we have R cap is 3.5 global plus user tendency 0.3, movie tendency 0.4 plus user movie interaction 0.86. R cap becomes 5.06. Now, if ratings are restricted to 1.5, we could clip this prediction to 5.0, or we can have a way of clipping it like that. So, how does the machine learn the factors? So, how does we are talking about Netflix now, which is a whole AI kind of system to match movies with users. So the latent vectors are initially known. We need to find UVBIBJ, that such that predicted ratings are close to observed ratings. So for each observed rating Rij, we calculate the prediction R cap sub ij, and the error E sub ij is equal to R sub ij minus R cap sub ij. So you can see this is a regular pattern, whether it is natural language processing, image generation, text generation, and things like this. Even in rating movies too, it's usually like we have a reality and we have a prediction, and we compare the difference between the two to compute loss, and we want to minimize that loss at the end of the day. So a common objective is squared error, so more like the maximum mean squared error that we talked about the other time. So in this case now we just have squared error. So the difference in the rating and the reality, we sum it all up, and we square and sum it all up, where omega represent the set of all observation or observed ratings. So we also add regularization now, so we can have we minimize the squared error, then we have a regularization. So lambda, I mean, the idea of regularization, you can see that a lot in things like ridge regularization, lasso, and even elastic regularization. So it adds some penalty to the to what you are do to the optimization problem. So this regularization, right, prevent the model from simply memorizing the training data. So that way, keep the system sane. Now, why do we need regularization here? Suppose a user has, now, by the way, this is the regularization part, this part now. This is the loss. This is the squared loss, the squared error we want to minimize. Then we add this penalization to ensure that the model does not simply memorize the training data. Now, why do we need regularization then? So suppose the user has rated only two movies. A model with too many latent factors could memorize those two ratings perfectly. So, and of course, that only two movies will be too small to do justice, right? But that does not mean it's understand the user's preferences for sure, and this will lead to overfitting. So, regularization adds a penalty for excessively large latent vectors. So, basically, regularization helps to prevent overfitting. So, when you have things like lasso, ridge, or elastic regressions, they help to prevent overfitting. So regularization adds a penalty for excessively large latent vectors, and the objective becomes this: that loss is the prediction error plus complexity parameter. So, or we can say L is equal to data error plus lambda times model complexity. So the parameter lambda controls the strength of regularization. So large lambda leads to simpler model, and small lambda leads to more freedom to fit the data. So we have large lambda leads to simpler model, and small lambda means there's more freedom to fit the data. Now, talking about learning the factors with gradient descent now. So the objective function, we know one of the most important algorithms in AI is gradient descent. So that it is what is used in the process of optimizing the loss, of minimizing loss, that is. So for a particular rating, E sub ij is equal to R sub ij minus mu plus bi plus bj plus u sub I transpose v sub multiplied by v sub j. So the gradient with respect to the latent vectors would then be dl dui, which will be equal to minus 2e sub ij v sub j plus 2 lambda ui, like that. So that's us differentiating L, which is the loss with respect to the to user biases, user parameters, and we have DL dvj for the movies. Now we get the same kind of expression. So gradient descent updates the parameters like this. So you have UI becoming UI minus eta dl dui. We've talked about this concept a lot. Eta is the training the learning rates, and then we have the initial value, and then we have the gradient of the loss with respect to the parameters for the user now. And then for the movie, we have the same kind of thing. So eta is the learning rate, and that has to be not too small, not too big as to cause oscillation of the values, and not too small to make the process of training the system of prediction too slow, right? So we can have a tiny recommendation system in Python like this. So import number as NP. So user stock item rating matrix is what we want to have now. So the zeros means unknowns, right? So we have this so we make five lists to make a matrix. So we have R is NP array, row one, row two, that's user one, user two, user three, user four, then movie one, movie two, movie three, movie four, movie five. Anyway, you see zero, that means the value of the rating there is unknown. So again, these two, for instance, means that user five rates movie four 2. right? And all the zeros mean that the users, the corresponding users have not rated the corresponding movies. So in this case, of course, this is just us outputting the matrix right here. And the next thing, we want to identify observed ratings now. So to identify the observed ratings, so we have locations of observed ratings now. The observed is actually np dot arg where r is greater than zero. Anyway, r is greater than zero. That is why we have ratings now. So something like 541, 412, 154, 342. So we want to pick this up. Now, the reason why this is important, for in a 5 by 5 matrix, or this is even a 4 by 4 matrix. So this is a 4 by 5 matrix. In a 4 by 5 matrix, it is easy to point it. But imagine you have a 10,000 by 1 million. So it will be hard to actually know that. So this becomes useful if you are dealing with a very big matrix that you cannot that you can't really visualize directly like this. So you can see the movies that have been rated. So we can then print observed ratings for I, J in observed. So the observed now. So we then have print F user I movie J. Then we have that. Rij. So we see that user zero, of course, in matrix counting start from zero. For instance, row one is actually assigned zero, column one is assigned zero also. So user zero, movie zero, that's this one now. The rating is five. User zero, movie four. I mean movie one because zero, one, two, three, four. Then zero, one, two, three, zero, one, two, three. So user zero, movie one, that's 4.0. Then user zero, movie three. This now that's one. User zero. Okay. I mean, we need only the movies that have been rated. That's why all the zero values, all the zero ratings will be filtered out. And that is what this R greater than zero is doing right here. np.arg where R greater than zero. That's what this exactly is doing right here. Now we then have so user three movie three. That's basically user four movie four, right? No, user four movie four. Yeah, user four movie four in that sense. One, two, three, four. One, two, three, four. Yeah, user four movie four. But because counting starts from zero in Python, that is 2.0, and that's exactly what we have right here. Now, you can then implement matrix factorization. So here, you of course, because some randomness will be involved at some point. So you see, randomness is here. So anytime you involve this random module or function like that, you want to seed it so to make sure you can always have reproducibility, so you can always get the same result. If not, you keep getting the same result because you have randomness here. So rating the matrix now. So you have this matrix, the rating matrix same as before, I think. Yeah, I think it's same as the one before. Yeah, 342. Yeah, down here 342. Then you now have number of users, number of items, and take the shape of the R we defined already. Then we came across R, we already defined R here, So then we have number of latent factors. So if we have number of latent factors to be two, that's K is two now. Then for random initialization, so we have U np.random. So this is following a normal distribution from 0 to 0.1. Then taking the number of users and K into consideration, V the same. Then we have hyperparameters like learning rate for the gradient descent is 0.01. Lambda for regulation, that's the lambda associated with the regularization part. This lambda here now, this lambda here, which is regularization to prevent overfitting. Then we have all that, and then number of epochs, so number of times that should be done, the training should be done. So train only on observed ratings, so only ratings that have been observed. Of course, you want to identify other ratings based on the ones already done. You want to identify the unavailable ratings based on the ones you already have. So for epoch in range epochs now, so for the 5,000 epochs, so for I and J in observed, so the prediction would simply be the dot product of ui times vj, like that. Then error, you have the error is Rij, whatever you get for the rating you get minus the prediction. Then you save old vectors now. So u old is ui, the copy, save it somewhere. V old vj dot copy, so save it somewhere. Then you have gradient updates now. So this is where the whole learning starts. So you have ui plus or minus. I mean plus equals. So that's like the ui is the initial one, and then uh, so whatever you get, you be a plus equal. So whatever you get, you add it to it and keep going. So you have vi learning rate multiplied by error times v old minus lambda reg plus v old, like that. Then the same for vj. So if epoch divided by 500 is zero, predictions. So in this case now, it means we have 5,000 epochs, but we only want to get results after every 500 epochs. So that at the end of the day, we don't have 0, 1, 2, 3 up to 5,000. It will be too many. But we just want to see the results after every 500 epochs. That's what this is doing. Because this one is doing an integer. What is this called now? It's doing a a modulo division, yeah, modulo division here. So if you divide by 500 and it perfectly divides, then give us the answer. So it means after 500, at 0, give us an answer. 500, give us an answer. 1000, give us an answer. Then give us this prediction, u multiplied by v transpose. Then the mean squared error now, you have the mean of Rij minus prediction, square that, and for Ij observed. So then you print the number of epoch and the mean squared error to go with it. So, and that is what also in trying to implement the matrix factorization. So we do that, and then the process starts. Okay, I ran it before. Oh, that was fast. Interesting. That was so fast. I was expecting that to show one. Okay, good. So we have that already. So epoch 0 MSC is 11.1930. So the error is large. So by the time we get to epoch 4,500, we have 0.013 like this. So now we have whatever we get at that point, the training is good now. So the error is minimized. So at the end of the day, we now want to examine the length matrix. So at the end of the day now, so the predicted R will now be U at U multiplied by V transpose, and then we print the predicted rating matrix now. That'll be so we round to two decimal places each predicted value of R because the training has taken care of all that here. So by the time we have put the matrix here, we have 4.96, which is still close to the original 5 we had in the original matrix. So 4.96. Then the next one is 3.96, which is also still close to that 4. And then here, I think we didn't have we did not have we did not have third and fifth rows. The third and fifth rows, now we have them as minus 1.08 and 1.32 like that. So, and then we have predictions for all the other parts. So what just happened? We started with R containing many missing values, and the algorithm learned the user behavior that's representing users in latent space, and V representing movies in latent space. Then we reconstructed R cap, which is U times V transpose. The reconstructed matrix contains predictions for both observed ratings and previously unknown ratings. Then the previously unknown entries are exactly what we need for recommendation. Therefore, missing matrix entries will correspond with predicted preferences. So then we can then recommend the best unwatched movie now. So using that, what we have done now, so using this matrix that we finally ended up with based on the training, so we can recommend the matrix movies that have not been watched but that are actually the best. So in that case, we recommend the best unwatched movie. So user 0, so for user 0, user ID is 0. That's first user there. Then the predictions. So we have predicted our user ID. So movies not yet rated. So on watch now be NP anywhere. Our user ID is 0, for the first user like that. So we rank on watched movies. So rank is equal to sorted movie, prediction of the movie for movie in unwatched. So and then we have the key. So at the end of the day, we have the ranking predicted, like the best unwatched movie. Okay, what happened here? What happened here? Okay, I did not run all this. I didn't run this. Yeah, so now we are good. So with that in place, we can then have this because this refers to that actually. So predicted R. So we also need predicted R right here. So predicted R user ID. So for movie 4, predicted rating is 1.34 for the first user. So we have movie 2, predicted rating is minus 1.08. So these are the best on watch movies. I mean, this doesn't make so much sense because these are the only two movies that have been unwatched. So if we're going to say best. Okay, best unwatched movie now. So movie, okay, I get it now. So movie 4 is predicted rating is 1.32. Movie 2 predicted rating is minus 1.08. So this 1.32 tells us that the best unwatched movie is movie 4, simply. So that way So the that user for the first user, I think if you want to recommend a movie for them, you just recommend movie four because that's their best unwatched movie based on their behavior and the kind of movies they like. So the complete recommendation pipeline is this. You have a simplified recommender system which can be viewed as user behavior leading to interaction matrix, leading to latent factors, leading to predictions, leading to ranking, leading to recommendation now. So user behavior, so use that to form an interaction matrix, some kind of user movie matrix, and then you have latent factors for the users and the movies. That leads to predictions, and then you rank, and then you recommend. So in step one, you collect interactions. Examples: watched movies, skipped movies, searched movies, rated movies, movies added to the wait list, completed movies, movies that were stopped early, like that. So I mean, YouTube, for instance, or Netflix can track these kind of things. So you can save movies to watch later and all that. Movies you've watched, all of the data, you have them. So in step two, you then construct user item interactions. So then step three, you learn latent representations. And step four, you predict user preference. Step five, you rank candidate items, and then you recommend the highest ranked items. Like what we did previously, the movie four will be recommended for user one. So let's see if we can. So this is user ID zero now. Okay, I was thinking I want to change that. Okay, for user one, that'll be second user going by Python counting. So for user one now, you know, so if we do this, so the predicted movie rating 5.05, that's movie one, and movie four is 2.74. So for the second user, one will be is their best unwatched movie. So let's take it back to what we had before. So we have this. So um and we've seen the complete recommendation pipeline, like the height all goes. Now, modern recommendation systems use more than ratings. You see, so a streaming service does not need to wait for a user to explicitly give a movie rating. It can observe behavior basically. So instead of you rating movies now, so your behavior is all modern systems like YouTube, Netflix, and all of them. For example, a user watches 95% of movie may provide a strong signal. All right. So if for a particular movie, a user watches 95% of it. Other signals can include just clicking the movie alone. That means they're interested in some ways, right? Then the search is the viewing duration, the completion, the repeated viewing, the browsing behavior. So adding a title to a list, abandoning a title, interactions with recommendations. Therefore, the matrix does not necessarily have to contain explicit ratings. It can contain implicit feedback. For example, R sub ij can be 1 if user interacted with item and 0 if otherwise. This creates a different mathematical problem from ordinary rating prediction. So we're not basically worried about rating. It's just about behavior. The clicks, the watched, the quickly abandoned, the finished movies and things like that. So explicit and implicit feedback. Explicit feedback, the user directly tells the system what they think. Examples, say Rij is equal to 5 or Rij is equal to 1. Like maybe like and unlike, these kind of things. Examples, you can have like star ratings, thumbs ups and thumbs down, likes and dislikes. All of these are, explicit feedback by the user. Then implicit feedback is also there. The system infers preference from behavior. Examples, you watch the movie, you watched repeatedly, you searched for a title, you clicked a recommendation, you abandoned the movie. The distinction is important. A missing interaction does not necessarily mean user dislikes the movie. It may simply mean user has never encountered the movie. This is one of the major challenges of recommender systems. Now, the question, why matrix factorization is so powerful? Imagine a movie has hundreds of observable characteristics. Instead of manually defining all of them, matrix factorization can discover a smaller latent representation. For example, V sub j is 0.91, 0.10, 0.73, 0.04, and all of that. That might represent hidden characteristics associated with a movie. And similarly, use of I can be 0.87, 0.15, 0.65, 0.02, which represents user preferences now. So the dot product measures how well the user's preferences align with the movie's characteristics. Therefore, recommendation is roughly latent preference matching. So you're just matching the latent preference of a user to the latent behavior of a movie, latent characteristics of a movie. So imagine this, visualizing latent preference now. So here we are importing matplotlib.pyplot as PLT. That means we want to visualize. So plot users now. So imagine plot scatter all the users for the first one, and then you have U I like that. So that's like first you two users. So this user one, user two. Then mark O. So you mark users as O, and then we have hundred of samples of them, and you label them users. Then you now say for I in range of the length of the users here now. So you plot a PLT annotates. So UI U10 UI1, and then you plot the movies too. So just like you did the scatter plot here. So PLT does scatter, that's scatter plus, and then scatter plot for movies too. So for first two movies, and then you also have 100 movies that way, or S is 100. So for J in range, L length of the V now for the movies, then you also annotate the M whatever, maybe M0, M1 like that, and then you run that, and you have a user movie latent space like that to match movies to users. Maybe not perfectly, but at least you can see which users are closer to which movies. So users and movies in latent space now. You have latent factor one, which explains most of the behavior, and you have latent factor two. So in this case now, user three is likely to watch movie two. That's what this means because they are close by. Then user two is more likely to watch movie four than movie one because movie four is closer to user two. Then user three is more likely to watch movie four compared to three, like that. So user one, user zero is most likely to watch movie zero. That kind of thinking is what you have right there. So at the end of the day, we have the geometry of recommendation. Matrix Matrix factorization converts users and movies into points in a latent space. So a user's position represents their hidden preferences. A movie's position represents its hidden characteristics. If a user's vector points strongly in the same direction as a movie's vector, their dot product tends to be large. So recall that U sub I transpose V sub J is equal to the modulus U sub I multiplied by modulus V sub J cos theta. Therefore, the prediction depends on the magnitude of the user vector, the magnitude of the movie vector, and the angle between them. When the vector aligns, we then have cos theta to be approximately 1, and the interaction tends to be strong. When they point in different directions, cos theta is approximately 0, then the interaction tends to be weaker. So this gives matrix factorization a beautiful geometric interpretation like that. So you see geometry coming into algebra and then helping us in machine learning and AI in general. So finding similar users now, suppose UA is 0.9, 0.8. That's user behavior now. User A. For user B, 0.85, 0.75. These users are close in latent space because 0.9 is close to 0.85, 0.8 is close to 0.75. Therefore, the system may infer similar latent representations, which implies similar preferences. So this is one reason collaborative filtering works. The system does not need a human to say Alice and Bob have similar tastes. No, you just need to calculate the dot product between this and see that it's really close to one. So the mathematical representation can reveal that automatically. So then, how about finding similar movies? The same idea works for movies now. Suppose V sub A and V sub B are close together. They have similar length representations. A recommendation engine can therefore identify movies similar to movies you already like, So because you always watch this, then this you may also like this based on that. So this creates the familiar recommendation pattern. Because you watched X, you may also like Y, like that. So that happens a lot if you're watching music videos. If you're watching the music videos of a particular singer or so, by the time you're done, there's a likelihood that similar songs from the same person will be recommended for you by the time you're done. I have that experience a lot on YouTube. The measuring similarity. One common similarity measure is cosine similarity, which we've been talking about a lot. So similarity between A and B is simply A transpose B. That's the dot product between A and B divided by the product of the moduli of the two vectors. So the value will always lie between -1 and 1. For many recommendation applications, the similarity of 1 means the vectors point in nearly the same direction, and we can use this to find movies similar to a movie that the user already enjoyed. So if it is closer to -1, then it means they don't really enjoy that. 0 means there's no connection. So movie similarity now. In this case, we have scikit-learn dot metrics of pairwise import cosine similarity, and then we have movie similarity. So cosine similarity of V, the V that was defined before now. So we print movie similarity matrix and we round up to two decimal places. So here now, the same table that was generated. So you remember 4.96. Oh, maybe I think this is different now. Where was the last V we defined? It should be for the last V that was defined. Yeah, so that's the V defined in this place here. This V right here, I believe. Yeah, this V here for movie similarities now. So we have all of that. And then you have 1, 0.6 to 0 minus 0.35 and so on. Then you can also recommend you can recommend similar movies in this case now. So for first movie now 0. So similarities, you have movie similarity ID with the movie ID 0, and then ignore the movie itself. So you have similar movies to that. Instead of that particular movie, just want to have movies with similar rating being used in this case now. So similar movies, you have J similarities, J for J in range, length of V now for the movies. If J is not equal to movie ID, so you're only recommending movies that are not similar, that are similar, not exactly this movie. So this line excludes any movie that is already that we are dealing with now. Movie 0, we are excluding it. Yeah, then looking at movies that look like it. So movies similar to movie ID. So by the time you run this now, it tells us movie similar to movie 0. So it tells you movie 1 with similarity of 0.615, and movie 3 similarity of 0.273, movie 4 similarity of 0.207, and movie 2 similarity of minus 0.349, like that. Then we have the cold start problem. Matrix factorization has a major weakness. Suppose a brand new user joins Netflix. So new to Netflix, the system has no history for that user. You can think the same of YouTube. So what is U new? The new value of the user behavior. We don't have it yet. So we do not know. So likewise, suppose a brand new movie is released. The system has little or no interaction data for V new. So this is called the cold start problem. So no information. This is called the cold start problem. This is called cold start. So there are two major forms here. You have the user cold start. A new user has little interaction history. Item cold start. A new movie has little interaction history. So real recommendation system therefore combine collaborative information with additional signals. So let's see. Recommendation systems are more complicated actually. A real production recommendation system can involve many stages. A simplified architecture, which is candidate generation leading to ranking and then re-ranking and then final presentation. So for candidate generation, you find a manageable collection of potentially interesting titles for that random candidate. And then the ranking, predict which candidates are most relevant. Then re-ranking, you apply traditional additional considerations such as diversity, freshness, availability, context, and user preference. Then you have presentation. Decide what to display and how to display it. So matrix factorization is therefore best understood as one important mathematical building block in the broader recommender system toolbox. So from prediction to recommendation now. Suppose the system predicts movie A, B, C, D, and E with preference value with predicted preference 4.91, 3.72, 4.68, 4.12, and 4.95. The system sorts them as E greater, of course, E is greater than A is greater than C is greater than D, and D is greater than B, like that. So the top recommendations will simply be movie E, movie A, and movie C. So will be the top three recommendations. Therefore, the uh, prediction will follow ranking and then makes recommendation. So this distinction is important. A recommender system does not merely predict ratings; it ultimately has to make a ranking decision. Now, how do we know the model works now? Suppose the true ratings are for four movies, 5432, and predictions are 4.8, 4.2, 2.7, and 2.1. We can calculate the error. So mean squared error is 1 over n. We are used to that. So Ri, so these values, so 5 minus 4.8, 4 minus 4.2, 3 minus 2.7, 2 minus 2.1. So each one like that squared and then added together and averaged, then we have the root mean square error. So that's taking square root of that. So smaller RMSE uh, means predictions are closer to observed ratings, like that. So we then have RMSE in Python. From sklearn of metrics, import mean squared error. So you have the actual, you have the predicted, and then you can compute RMSE directly. So RMSE gives us 0.2121. So RMSE means predictions are closer. Smaller RMSE means predictions are closer to observed ratings now. So this is small, of course, not if we compare it with another one, we can know which one is better. Then we then have some recommendation matrix. A recommender system may care more about ranking quality than exact rating prediction. So important metrics then in that case then include precision at k. So precision at k on the top K recommendations, how many were relevant? That's what prediction at K deals with. So precision at K is simply relevant recommendations in top K divided by all the possible K available. And then you also have recall at K. So we know precision and recall for many, I think especially I think unsupervised learning also, I'm not sure now. I think one of those, especially unsupervised learning, I think. So you have precision, you have recall. So how many of the relevant items are successfully recommended? Okay, so recall at case, then relevant items retrieved all over all relevant items. And then you have the NDCG. So normalized discounted cumulative gain gives more weight to highly relevant items appearing near the top. Thus, good recommendation is not only equal to it's not only low RMSE. So there may be low RMSE, but the other factors are involved. So that's why we talk about other metrics like precision at K, recall at K, and NDCG. So the final objective is useful ranking and good user experience at the end of the day. So imagine we have a small end-to-end example, import number as NP, and we have a user matrix like the matrix we had before, the initial matrix when we started. Then you have number of users, number of items following the R shape now. So that we have that'll be four users, five items, four users, five movies, and K is equal to 2. So initializing latent vectors now. So you do the seeding to ensure once you are going to use any random thing, you have to seed it to ensure that it is reproducible so that you don't keep getting different answers. Because anywhere you call random, each time you call it, you are going to get different results. But if you seed it, you are going to get the same thing all the way. So you have np.random.seed for the two, then you have the user behavior and movie characteristics here, and then you train the parameters learning rate 0.01, lambda this for regularization 0.02, 5,000 epochs, and then for the observed now you just have everywhere r is greater than 0. Then you have the matrix factorization now, which is about the epochs. So prediction, you have the dot product of ui and ui and vj, and error, you have rij minus the prediction. Then you copy this and you keep updating, and then you reconstruct the matrix now to get the predictions for places we don't have this where this is happening. Reconstruct matrix, you have the original matrix, and then the predicted matrix can then follow. Then we then generate recommendations based on all of that. So for user and range, number of users now, so you have candidates, movie, r hat, the user and the movie. For movie in range, number of items, that's number of movies available. So if r is user comma movie equals 0, like that, then you have so movie can you can sort the candidates now, and then you have all of this. Then you print the recommendation for each user. So for movie, score in candidates, print movie and predicted preference. So using all of this, then we can have we can run this. We run this now, and we get our result here. So see the original matrix. That was what we started with, the predicted matrix. That's what we predicted. Then recommendations for user 0, just like we saw before, movie 4 is better predicted. That's 1.32 followed by movie 2. Of course, there are only two movies that were not known here, this and this. But movie 4 is better, is definitely better than movie 2 for this user. So this movie is predicted for user 1. Which is 0 in Python, right? Then you have recommendations for user 1. For user 1 now, so movies 1 and 4 were unknown, or if you like, if you want to count normally, that's 1, 2. So 2 and 5 were not known. So, but here, let's say it's 1 and 4, right? So for user 1 now, the predicted preferences are 5.05 and 2.74. So it means that movie 1 is predicted for user 1. That's 0, 1 now, or user 2 if you're going to count normally. So for user 2 now, that's user 3, that's this user. So we had 0, 1, 2, 3. 2 and 3 were missing. So but 2 rates higher. So this movie is predicted for user 1 like this. So because it has 3.8 as rating. Then movie 3 predicted. Okay, yeah, I mean we've done that. Then for user 3 now, that's the fourth user if you count normally 1, 2, 3, 4. So for user 3, movies 0 and 4 were unavailable, but movie 4 is ranked 3.12, so it ranks better. So for user 3, we recommend movie 3.12, and that's how this goes. So the big mathematical picture then is this: the entire idea can be summarized as R is approximately UV transpose, where R is observed user item interactions, U is latent user representations, and V is latent item representations. So for a particular user movie, R cap sub ij is U sub I transpose V sub j. So with biases, R sub ij cap is mu plus bi plus bj plus u sub I transpose v sub j. So the model learns u and v by minimizing prediction error. So we have this now, which is there's regularization here. So then we have predictions, ranking, and recommendations. Now, the question is why this is AI? Why is this AI? Matrix factorization demonstrates a fundamental principle of machine learning. We do not explicitly program every preference. We learn hidden structure from data. Nobody tells the model Alice likes science fiction. Instead, the model observes behavior. Alice watches A. Alice likes B. Alice skips C. Alice watches D. From from many of such observations, the model then learns the behavior of Alice and a latent representation of Alice's preferences. Then likewise, it learns the movie characteristics for every movie. So the recommendation emerges from their interaction. So yeah, the user Alice's behavior multiplied by movie characteristics. This is one of the most beautiful ideas in applied machine learning. So you have the behavior, and then you have a hidden structure, which is the latent space, and then a prediction comes out from that. And then you talk about matrix factorization and embeddings. So this is a deeper connection. There's a deeper connection between recommendation systems and modern AI. Matrix factorization creates vectors UI and VJ. These vectors are representation of user items. So users and items rather. So this is closely related to the broader idea of embeddings now. So an embedding converts an object into a numerical vector. We saw this a lot in earlier videos. For example, you have a movie with this embedding 0.81 and 0.1 to 0.43, and a user has the following preferences. So once objects are represented as vectors, we can use dot products, cosine similarity, distances, nearest neighbors, clustering, and neural networks, which are all machine learning stuff. Of course, these are more mathematical, but clustering neural networks and nearest neighbors take those mathematical ideas into the realm of AI. So this same representation learning philosophy appears throughout modern AI. So this same representation learning philosophy appears throughout modern AI. So we have from scores to probabilities now. A recommendation model can produce a score S sub ij, but sometimes we want the probability that the user likes the item. For example, probability Alice likes movie X is 0.92. One way to convert a score into a probability is the logistic function sigma of X, which is we encountered it as an activation function when we started out. That is equal to 1 over 1 plus e raised per minus X. Then we say probability of Yij equals 1 is equal to sigma of Ui transpose U sub I transpose multiplied by V sub j, where Yij is equal to 1 in this case, could mean that the user interacted positively with the item. This connects recommender systems to probabilistic machine learning. So we see all of this coming together. So see an example. Suppose the model produces S is equal to 2. Then we have probability Y equals 1 is equal to 1 all over 1 plus e raised per minus 2. So approximately probability y equals 1 is 0.881. So the model estimates about an 88.1% probability of a positive interaction between a user and a movie. So if s is minus 2 on the other hand, then probability y equals 1 is approximately 0.119, because if you put this here, you have 1 over 1 plus e raised per 2. So thus the model can transform latent compatibility into a probability-like preference score. So and that's how we move from scores to probabilities now using the sigmoid function. So applications of recommendation systems now. The same mathematics appears in many domains, like in streaming, where we can talk about recommending movies, shows, and music. I keep using the example of YouTube in addition to Netflix that we're considering here. Then for e-commerce, you can recommend products, accessories, and related items. Social media can recommend post accounts, communities of videos based on the kind of things you interact with normally. Then you can have online learning like courses, lessons, exercises, learning resources. Then scientific discovery like papers, genes, molecules, and experiments. Job platforms, job candidates, professional connections. The general problem is, given what we know about the user, what should come next, basically. That's why when you finish watching a YouTube video, you have recommendations or as to other things you may be interested in. So talking about the limitations of matrix factorization now. Matrix factorization is powerful, but it has limitations. Cold start. So new users and new items have little interaction data. That's cold start. Then sparsity. Most user item combinations are unknown because you have only, as a user, maybe you have only watched few of the most of the tons of available movies or things like that. Then you have the popularity bias. Popular items may receive disproportionately many recommendations for sure. And you have lack of explainability. A latent factor such as I3 is 0.2 may not have an obvious human interpretation. Then changing preferences. A user's taste can change over time. So I liked something last year. This year I may move on to something else. Then the static vector may not capture this, that kind of changing preferences. Then you have the context. Preference can depend on time, device, location, current activity, season, social context. Therefore, modern recommender systems often incorporate temporal, contextual, sequential, and neural models. So trying to capture the changes that are also happening. So for matrix factorization to modern recommender systems now, the historical progression can be viewed conceptually as this. So it started with popularity. So popular things will be recommended. Then we moved on to collaborative filtering. That okay, this person liked this and this movie and that movie. So based on this movie, these two movies look alike. Then we can recommend this other one. Or these two users they like these two movies, so we can recommend this kind of thing for them. Then matrix factorization followed, and we have embeddings, and then we have neural recommendation, and increasingly we have sequential plus contextual plus multimodal recommendation. So that takes care of changing preferences, for instance. So the mathematics becomes more sophisticated, but the fundamental question remains: what item is most relevant to this user right now? That is the idea. So the core lesson we are learning is Netflix does not need someone to manually create a list saying Emmanuel will like this movie. No. Instead, a machine learning system can learn from patterns of behavior. So the fundamental mathematical pipeline is user behavior leading to interaction matrix. That is user movie matrix like that. So then we have R is approximately U V transpose. Then we have a rating R cap underscore IJ equals U sub IT multiplied by V sub J. Or with biases, we have R caps of IJ, that we have the general rating, the global rating, the user bias, the movie bias, and then we have the interaction itself. Then we have predictions leading to ranking and ranking leading to recommendation. So the deeper idea is that a huge matrix can hide a much smaller structure. So matrix factorization discovers that hidden structure, and that is the mathematical heart of many recommendation systems. So the mathematical heart of many recommendation systems is matrix factorization, which reduces a very huge matrix, which extracts the most important information in a very large matrix. So some key takeaways. A recommendation system predicts what a user may prefer. User item interactions can be represented as a matrix R. Then the matrix is usually sparse, that is, there are too many unknown values. Then collaborative filtering learns from patterns across users and items. Then matrix factorization approximates R to be UV transpose. Then each user receives a latent vector U sub I. Each item receives a latent vector V sub J. Maybe it's a movie, a job, or whatever, or a page on social media. A basic prediction R caps of IJ is UI transpose multiplied by V sub J. Then a more realistic model includes the one that incorporates biases, general rating, user bias, movie bias, and all that. Then gradient descent can learn the latent factors. Then the learned vectors can be interpreted geometrically as points in latent space. Similar vectors often correspond to similar preferences. Missing matrix entries can be converted into recommendations, and then we can have real recommender systems going beyond matrix factorization and combining many signals and models. So the deeper AI principle is you have observed behavior leading to latent representation, leading to prediction, and leading to a final decision. So we have 20 practice problems now. Um, because of time, I guess it is better not to, I mean, not bother with solving any of the problems. But there are concepts you already know, the whole dot product kind of thing. So I was supposed to solve problems 14 and 18. But because of time, I think I'll just show the questions and move on. Okay. Um, so you have problem one showing clearly here. Problem two, or can we see two and three together? Okay, let's just focus on two. So you have problem two here. Three, four, five. Or can we see five and six? Yeah. Five and six. Yeah, five and six can be seen here. Then seven. Okay, let's just focus on seven here. Then eight. 9, 10, 10, 11. Or can we see 11 and 12 together? No. 11, let's focus on 11. 12, 13, 14. Yeah, I was supposed to solve this 14. So you want to try that out since I'm able to do it now. Then 15, 16, cold start strategy. A new person gets on a platform, or a new movie is released, or a new thing is released. So initially it's hard to know what's going to happen, but as they begin to interact with the system, you can then begin to learn their behaviors. So we can see 18 and 19 here. And then 20. Wow, 20 is so big. Okay, let me show one part of 20. This one part of 20. And then that. All right, let me know how helpful this is for you. If there's something that you let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is a good time to go ahead and subscribe. And of course, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.